So it's my pleasure to be here to talk about our work on how an IoT botnet of high wattage devices can disrupt the normal operation of the power grid and cause a large scale blackout. This is a joint work with Pritik Mittal and Vincent Poor, also from Princeton University. So as you all know, power systems are one of the most essential infrastructure systems. The National Academy of Engineering named electrification as the greatest engineering achievement of 20th century on top of computers and the internet. These systems consist of different components. First are generators that convert energy from natural resources into electricity. Then there are high voltage transmission networks that deliver electricity from generators to distribution system of a town or city. And then there are distribution networks that provide electricity in various voltage levels to industrial, commercial, and residential consumers or loads. The term power grid is mainly point to the transmission network, and all the other components are usually lumped into components within this transmission network. To show you an example, here is North America Transmission Network, which is the largest running machine in the world. It consists of about 70,000 lines and 55,000 buses. If you're not familiar with the term buses, you can think of it as the nodes that are in this network. Beside these power grid physical infrastructure, these systems are controlled and monitored by SCADA systems that are supervisory control and data acquisition systems that are shown to be vulnerable to cyber attacks in the past couple of years. The most infamous of these examples are the cyber attack on the Ukrainian SCADA system that unplugged about 200,000 people in December 2015. In another recent report that's been shown that attacks on the SCADA systems in the smaller scale are more pervasive in the US grid. It mentioned in the report that hackers are developing a penchant for attacks on energy infrastructure because of the impact the sector has on people's lives. In another recent report by Department of Homeland Security, it has been indicated the hackers could get access to the SCADA system of US power grid, and they got to the point where they could have thrown switches and disrupt power flows. Inspired by all of these events and motivated by all of these, there has been a lot of effort to improve the cybersecurity of power system. However, most of the security work has been on the power grid physical infrastructure as well as on its control network. And they were all based on the assumption that the power demand can be predicted reliably on hourly and daily basis based on the historical data as well as data such as weather data. However, with the growth in the number of Wi-Fi-enabled high-wattage IoT devices, such as air conditioners and water heaters, we were wondering, is this still a safe assumption or not? To answer this question, let's look at some of the numbers. Here's the table shows the power usage of most common appliances in the households these days that nowadays they are also Wi-Fi enabled. On top, we have air conditioners that consume about 1 kilowatt instant power. And on the bottom, we have more energy-hungry devices such as electric water heaters and electric ovens that consume about 5 kilowatt of instant power. If you look at one of the largest botnets in the past couple of years, the Mirai botnet, which consists of 600,000 bots, and multiply this by the consumption of electric water heaters, we'll see that a Mirai-sized botnet of water heaters can change the demand instantly in an area by about 3 gigawatts. To just give you a sense of what does it mean, it is similar for an attacker to get access to the largest currently deployed nuclear power plant in the power grid. So based on this, in this work, we introduce a new threat that we call manipulation of the demand via IoT devices, or MadIoT attacks. And we demonstrate that high wattage IoT devices, once compromised, they give an adversary a unique capability to manipulate the demand in the power grid and potentially cause a blackout. To illustrate this via a figure, here's the small figure of the power grid, and here are the high wattage IoT devices that are connected to the power grid via distribution network. An adversary that can get access to these high wattage IoT devices, and if there are sufficiently many, it can manipulate the demand in the power grid by synchronously turning these devices on and off. Such an attack will have several consequences on the normal operation of the power grid. In particular, here is the frequency response of the power system to such an attack. As you all know, in North America, power system operates in 60 Hertz, so before any attack, the frequency should be around 60 Hertz with a small fluctuations. At time zero, the attacker increased the demand instantly, which subsequently results in the frequency of the systems to drop. This drop in the frequency of the system is due to the change in the rotating speed of generators, rotors, that compensate for the extra demand with their inertia. And if this drop in the frequency is significant, it causes the protection relay to disconnect the generators from the grid in order to protect the hardware. That, as a result, it may cause outages. So the first consequences of MadIoT attack is the frequency instability in the system. However, if this drop in the frequency is not significant and the system have enough inertia, it can compensate for the extra demand for a short amount of time until the primary controller of these generators start operating. The primary controllers then increase the power input to the generators in order to increase the generation and compensate for the extra demand. And they can stabilize the frequency within several seconds. However, since this change in the power supply and demand are not prepared, are not planned by the system operator, they can result in several line failures, and these line failures can initiate a cascading line failures that may lead to a larger scale blackout. Therefore, the second consequence of these attacks can result in the blackout as well. Finally, if these attacks do not result in any damage to the network, since the system operator needs to compensate for the demand through deploying more generation, they may lead to increasing the operating cost of the grid, which is the third consequence of these events. To go into details of any of these consequences, we did several simulations and several cases. Here are present some of the work that we've done here. So we've done some simulations on a WSSC 9-bus system, which is a small system, but it's a benchmark in power community. We analyzed two cases, one when the attacker increased the demand by 20% and when the adversary increased the demand by 30%. And we consider two cases when the grid has low inertia and when it has a high inertia, meaning it has enough generator to temporarily compensate for the extra demand. For example, you'll see that when the system have low inertia, 20% load increase may lead the frequency of the system to hit this critical under frequency generation tripping area, which cause the generators to get disconnected from the grid and cause a blackout. We also observed that 30% load increase in the grid lead both cases to reach this critical area and cause larger scale blackout. So effectiveness of an attack on the frequency of the system depends on the attack's scale as well as the system's total inertia at the time of an attack. And sufficiently large simultaneous increase in the demand can result in significant drop in the frequency of the system and cause generation tripping. As I told you earlier, if this drop in the frequency doesn't result in the under frequency generation tripping, it may result in line failures. For analyze this, we study a case in Polish grid 2008 grid, and we look at the case in which the demand only increased by 1%. For such an attack, the attacker requires about 200,000 smart ACs. And we observed that after such an attack, there would be several initial line failures, and after these line failures, they get removed from the grid through protection relay, and therefore they result in several other line failures that are in the second step, and such a cascade of line failures may develop for 5 stages, and it result in a 263 line failures and 86% outage. Therefore, only a 1% increase in the demand in Polish grid 2008 can initiate a critical cascading line failure. We repeated these simulations on the snapshot of Polish Grid 2004 and saw that for causing the same level of damage, this time the attacker needs to at least increase the demand by 10%, which requires about 2 million ACs, which is a significant number. To show you why why Power Grid 2004 is more robust against these type of attacks, we look at the histogram of the Polish grid lines power flow to their capacity ratio in summer 2004 and summer 2008, and we observe that there are more lines that are operating near their capacity in summer 2008 compared to summer 2004, which describes why the system is more vulnerable to this type of attacks. Therefore, it is important how saturated the power lines are at the time of an attack. This can provide some insight that how we can protect the grid against this type of attack. However, what we observed here is that attacks resulting in cascading line failures in general require fewer number of bots than the attacks resulting in critical frequency disturbances. Another way an attacker can result in line failures is to attack tie lines. Tie lines are usually high capacity lines that connect neighboring states or neighboring countries, and they are usually carrying large amount of power flow that are exported from a state or they are imported. An attacker can cause failures in these tie lines by increasing the demand in the receiving end of these tie lines and decreasing the demand in the sending end. We look at the hypothetical scenario which connects 5 countries, for example, and we observe that by increasing the demand by 1.5% in the yellow area and decrease the demand by 1.5% in the blue area, we can cause line failures in both of these tie lines. After such a failure, this can result in a huge imbalance between power supply and demand in the both areas and trigger a frequency stability or another set of cascading line failures. If you look at the history of the blackouts, it is similar somehow to the scenario that happened in Italy in 2003, that started with a failure in a tie line, and soon the initial failure triggered other failures in other tie lines in Italy that resulted in a larger scale blackout that time. And finally, as I said earlier, if the attack doesn't result in any damage to the grid, it can result in the increase in the operation cost of the grid, or the adversary's attack may be for the benefit of the particular player in the electricity market rather than damaging the infrastructure network. We did several simulations, but to cut the story short, we observed that in some situations, only 5% increase in the demand can result in 20% increase in the operating costs, which is a significant amount. To give you a summary of the number of bots required to cause these damages, here we assume that all the bots are air conditioners that consume 1 kilowatt, and we show this botnet size by bots per megawatt. Therefore, we normalize them by the size of the grid. On the top, we see that to cause a critical frequency drop, significant number of bots are required. However, for causing line failures and increasing the operating cost of the grid, much fewer number of bots are required. In this research, we only use publicly and freely available test grids not to reveal any vulnerabilities of real grids. Therefore, these numbers may be quite different for different grids with different characteristics, with different inertia and different topology. Therefore, more detailed analysis on the effect of MadIoT attacks should be performed by system operators to detect the robustness or vulnerability of their own systems. Moreover, as you can see, for causing critical frequency drops, substantial number of IoT devices are required. And since they should all be in the same geographical area, they might not be easily achievable by an attacker. However, with the growth in number of IoT devices, it is easier to achieve these numbers a few years from now. Now, in order to see how we can protect the grid against these type of attacks, I should mention some of the unique properties of these attacks that make them very hard to defend against. First property is that these attacks are indirect, meaning that the attacker doesn't need to get access to the SCADA system, and it can attack the grid only using the IoT devices. Second, it is very hard to detect and disconnect these devices for the system operator, because they are distributed and the system operator doesn't have access to the data of these IoT devices. Third, they are easy to repeat, therefore the attacker can repeat these attacks until they are successful. And fourth is that they are black box, meaning the adversary doesn't need to know the underlying topology of the grid or the detailed operational properties of the grid. And because of the third property, it can just repeat these attacks until they are successful at certain time. And the final property that can be solvable is that the power grids currently are not prepared to defend against these type of attacks. And these type of attacks are not part of their contingency list. So this can lead us to some ideas on how we can protect the grids, but at least increasing their preparedness against these type of attacks. For doing so, the first thing is that the system operators can improve the frequency stability of their systems by account for this type of attacks and operate their system such that they have enough inertia and there wouldn't be a critical frequency drop in their systems. They can also use devices that provide virtual inertia, such as flywheels and batteries, to increase the total inertia of system at a lower cost. The line failures can also be prevented if they operate their system on the operating point such that no lines get overloaded after such an attack. However, it requires solving a non-convex problem. However, in a recent work, we developed new tools to find such an operating point efficiently in polynomial time, which is the paper which is available on arXiv. Finally, they can remove sensitive online data such as power flow on the tie lines in order to prevent attackers to use this data in order to make their attacks more successful. To conclude, we believe that protecting the grid against MadIoT attacks requires effort from both power systems community as well as system security communities. We believe that power system operators should rigorously analyze the effect of potential attacks on their systems and with the help of researchers develop new methods to protect the grids against these type of attacks. From the IoT security perspective, we showed that insecure IoT devices can have devastating effects that can go beyond individual security and privacy losses. Therefore, rigorous pursuit of security of IoT devices, including regulatory frameworks, are needed. And finally, we showed that interdependency between infrastructure networks may lead to hidden vulnerabilities. Therefore, system designers and security analysts should explicitly study threats introduced by interdependent infrastructure networks in the future. With this, I would like to thank you all and would be happy to hear your questions. Thank you.
Hi, Bill Cheswick, University of Pennsylvania. Thank you for an appalling new threat model, the Internet of High Wattage Things. One of the loads that could be turned on that isn't on your list yet, but probably will be in the coming years, is charging electric cars, which often do not get a full charge. You charge 3/4 of the way, and they would not notice or mind if the charger was turned on for a minute all of a sudden.
Sure.
And so it'd be nice if the auto guys were even more secure than they're supposed to be now.
Absolutely. So it's a huge headache for power system operators, the electric cars, as it is, even in the distribution network. Assuming that all the cars going to the MetLife Stadium to watch a football and they all want to charge their devices.
Yeah.
Or they bought their cars, they instantly overload the distribution network. It doesn't even get to the transmission network, which is a great comment and it should be considered. Thank you.
Hello, I'm Shunan Liu from China, an undergraduate. So I'm very curious about the controller in the power networks, because the frequency must be synchronized. So did you take some considerations on the controller?
So we considered some, but we didn't get into details of the asynchronous consequence of these type of attacks that may really make these attacks more significant, because after these frequency disturbances, these generators may run into asynchronous frequencies. That again, it's another type that may lead to the blackouts, but we didn't get a chance to look at them more carefully. But it's a great question. Yeah, it's part of the future.
And I also wonder that I noticed that in our daily life, when we turn on air conditioners, it requires several times for us to. So this can now lead to an abrupt. So what did you deal with that question?
So we also mentioned this is part of the things that make attacks on the frequency of the system harder. But this delay doesn't prevent line failures because they're the same. So you just increase the demand. They are unplanned. So basically you change the power flow on the grid. So it doesn't change the second and third consequence of these attacks. But you are right, for the frequency, ACs might be very difficult to be used, but water heaters doesn't have this problem because they are purely resistive. So there is no delay for them.
Okay, thank you.
Sure, thank you.
Hi, Phoebe Rouge from the Federal Trade Commission. I was just curious about what about things sort of like at the endpoint, for example, circuit breakers and any sort of regulation that might be on the devices themselves built into sort of their power regulators that might help mitigate some of these sorts of things. If there's, because I mean, if you turn on a lot of high wattage devices in a small room, you know, you can blow a circuit breaker or whatever. Do those things play a role here?
I'm not sure. So you're saying if new regulations is good, or you're saying if
I mean, in terms of like, you know, if you had different tolerances in terms of the electrical systems that are required to be in houses or something like that. I'm just wondering sort of that level of entry into the power grid. Are there things that can be done at that level?
I'm still not sure if I understood your question.
I guess the question is just, so does the fact that there are circuit breakers that prevent you from having a very high spike in voltage in your home, does that play any role here?
So I think the main reason here is that they're distributed. It doesn't really overflow your internal circuitry, but as they aggregate and they reach to the transmission network, they increase the load within a city. So in the distribution level, they don't trigger any circuit breakers because they are the normal usage that can be used in the very hot summer day. The distribution network can already handle those power usage. But if it is not very hot day and you instantly, turning all of those, it is where it is unexpected.
All right, thanks.
Sure.
So we can take one last question.
I'm sorry.
Yeah. Hey, I'm from Georgia Tech, and I have a question about the feasibility of such attacks. Usually, the residential consumption of power inside the power system is less than 30 or 40%. So changing the power demand in 20% with the residential customers is very hard. So I was curious.
Yeah.
So if you want to, for example, change the 20% of the total demand by only the residential customers, you have to change the residential consumption by 100%.
Yeah.
So
we totally agree in this sense. For the causing frequency again disturbances, it's very difficult. The power grids are already protected against losing a single generator, for example. But you can add to this some of the IoTs that are used in the industrial level for the automation. So if those can also be considered, they can increase the possibility of these attacks. We're happy that they are not feasible at this current moment, at least for frequency disturbances. But we believe that in the future there would be more ways to increase the demand. Again, using industrial factories, you can use all of those devices. And the line failures, again, they require much less number of devices, which is 1%, which is feasible using these devices.
Okay, and another question, actually, it's about the, maybe I can ask.
Yeah, we can take this offline if you want.
Thank you.
This is our real last
Sandeep Kundu from National Science Foundation. I had two quick questions.
Sure.
The first question is, in your simulation of the power grid that you did you just apply a step increase in the load, or did you actually consider the transient behavior?
So we did a step increase in the load, but we also did the step. So when you do the step-by-step increase, the drop in the frequency is not as significant, which is what we expected. But if you do this step, which is hard to, again, get, this is what we did in the frequency analysis.
Yeah, okay. So normally in an AC, we'll have a transient behavior in the load.
Absolutely.
My second question is, that in a smart grid, there's a lot of energy storage systems, which is controlled by the power company, the grid operator. So as you're adding load, they will be controlling those to shed load.
Yes.
So did you consider that?
So this was a trick that we also mentioned in the paper. So we don't believe that load shedding is the best strategy here, because then the attacker can turn off those devices and cause a frequency overshoot. If you look at the paper, we believe that it's better to operate the grid in an operating point that doesn't get overloaded in any sense, that doesn't require load shedding, because load shedding can complicate the things. Yeah.
Okay, let's thank Saleh again.